Yo, what's up everyone? Welcome to the last lesson of thermodynamics. Today we're gonna just do a bit of practice with the whole topic. And the way we're gonna do that is that we're gonna go over the thermodynamics section of the 2020 local test. So that's gonna be from question 19 to 24. Let's just get started with question 19. For which reaction is the change in enthalpy of reaction equal to the change in enthalpy of formation for CaSO3 solid? So for enthalpy of formations, you need to see what are the elemental things that make up this compound right here. And so that's going to be calcium, it's going to be sulfur, and it's going to be oxygen. So what are the standard states of these things? Well, calcium is just going to come on its own as a solid. Sulfur is actually going to come in 8. It's also going to be a solid. And oxygen is going to come in 2, and it's going to be a gas. These are the standard states. So, and when you are calculating the enthalpy of formation, this thing over here, that degree sign, tells you that we're dealing with standards. So what you want to do is set the products equal to the compound that you want. So it's going to be like this, and you're going to make it out of calciums. You're going to make it out of S8. Sorry, that should be an S8. Let me just erase that really quickly. Okay, S8, and it's going to be out of O2. And that's somehow going to form this. So what are the coefficients that we need? Well, calcium is already balanced, so we can just leave calcium as is. We need 1 sulfur, so let's add a 1/8 on in front of here, and we need 3 oxygen, so let's add a 3/2 in front of the O2. And this entire reaction is going to be the reaction that's going to form calcium sulfate. I don't even know what this is called, but that reaction is answer choice A. And that is the correct answer. Let's move on to question 20, which tells us a 1 gram sample of ice at 0 degrees Celsius is placed in 50 grams of water initially at 25 degrees Celsius in an insulated container. What is the final temperature after the system has reached equilibrium? And it tells us the enthalpy of fusion for water, or for ice rather, and that's going to be 6.01 kilojoules per mole. So this question, we have two systems. First of all, it's going to be the system of the ice, and it's going to be the system of the water. And the system of the ice is a 2 gram sample, and it's initially at 0.0 degrees Celsius, but the water is 50 grams, and it's initially at 25 degrees Celsius. And we've done questions like these before, and from that we know that there's going to be an energy transfer between them, right? Water is going to lose energy to the ice, and ice is going to take the energy. And that's because water is at a higher temperature than the ice. So the Q of ice, let's let that be X. That should be a Q, not a G. It's going to be X, and the heat of the water is going to be negative X. Q equals negative X. Well, let's calculate Q for the water. So Q equals mc delta T. The mass is 50. The specific heat capacity is 4.18. That's the specific heat capacity of liquid water. And the change in temperature is going to be final minus initial. We know our final is going to be F, and our initial is 25. So essentially in all this, we're trying to solve for F. And now that we have calculated the energy of the water, let's calculate the energy of the ice. And as it turns out, it's really not as easy as the first one that we did, the water, because there's actually two energies involved in the ice. First of all, you're going to have the energy change from, because it's going from ice to liquid water, and there's actually an energy involved in that. And after the energy that it takes to melt it, you need the energy to raise the temperature. So you need the energy of melting, and then you need the energy of heating it up. So heating. And so what are the energies of melting and what are the energies of heating? Well, we can calculate them separately. Q of melting is going to be the mass, 2, times the change in enthalpy of fusion. And so since we know that it's 6.01 kilojoules per mole, we have to calculate how many moles are in our 2 gram sample. Remember, it's going to be 2 grams, and then our molar mass of water is going to be 18. So really, we're going to have 1/9 moles. So 2 times 1/9 times 6.01 kilojoules. And that's going to be the energy associated with changing the ice into liquid water. For the heat of like I guess heating it up, it's going to be heat equals mc delta T, just as we did for our water. So we're going to take 2 grams of it, and it's in liquid water form, so we can use the specific heat capacity of liquid water, and we multiplied that by the change in temperature, which is going to be the final minus initial, which at this point is going to be 0. So that's just F, but I'm going to just leave the 0 there just because. So now we can take this all together, right? So we can take 2 times 1/9 times 6.01 kilojoules. We can add that to the 2 times 4.18 times F. And what we have to do is that we have to set this equal to the negated value of this value that we found right here. So that's going to be negative 50 times 4.18 times F minus 25. And from this point, it's just you plug stuff in and you solve for F. And once you do so, you're going to realize that F is 21 degrees Celsius, and that's answer choice A. And we are correct. Actually, a little correction here. This 2 should not be there. That 2 would represent the grams, but we already converted the grams into moles. So if you did, I guess, I'm sorry if you did the reaction, if you did the equation with the 2, but it should be 1/9 times 6.01 kilojoules, which you would actually have to convert to joules, so that would actually be 6,010 joules. And once you solve for that, you will get 21 degrees Celsius. Okay, let's move on to question 21. Ethanol has a normal boiling point of 78.3 degrees Celsius and a standard heat of vaporization of 38.6 kilojoules per mole. What is the vapor pressure of ethanol at 45.0 degrees Celsius? This is going to be one of our classic Clausius-Clapeyron equation problems. So remember the equation, the natural log of the first pressure over the second pressure is going to equal the negative heat of enthalpy of vaporization over the gas constant times 1 over temperature 1 minus 1 over temperature 2. So in this case, our first temperature 1, would be 78.3 degrees Celsius. 78.3 degrees Celsius is going to come out to 351.3 Kelvin. So that's our first temperature. And then our first pressure is going to be 1 atmosphere. The reason it's 1 atmosphere is because it says normal boiling point. And normal boiling point is always recorded at 1 atmosphere. From here, we can fill in a couple more variables. Our enthalpy of vaporization is going to be 38600 joules. R is obviously 8.3145. And then our temperature 2 is going to be 45 degrees Celsius, which comes out to 318 Kelvin. And so essentially what we're solving for is the second pressure. The second pressure is unknown and we have to solve for it. So let's plug in all the information that we know. Pressure 1 is 1. We're solving for pressure 2. And then minus 38600 over the gas constant. And then 1 over temperature 1. Temperature 1 is 351.3. And then minus temperature 2, which is 318. And then once you solve for P2, you're going to realize that P2 is 0.25 atmospheres. And essentially, this is just all like just algebraic manipulation. If you just plug it into some do some calculator stuff, you'll be able to figure it out pretty easily. Okay, 0.25 atmospheres is answer choice A, which is the correct answer. Let's move on to question 22, which says, if the average carbon-hydrogen bond dissociation enthalpy in ethane is 416 kilojoules per mole, what is the bond dissociation enthalpy of the carbon-carbon bond in ethane? Ethane is going to look like this. So CC, and then it's going to be 6 hydrogens over here and over here. So what you can see from this is that there's 1, 2, 3, 4, 5, 6 CH bonds. 6 CH bonds. And there's going to be 1 carbon-carbon bond. Remember, the change in enthalpy of the reaction is just equal to the sum of the bond dissociation and energies. And so what we really need to do is figure out what this value is, the change in enthalpy of the reaction. And if we're looking for the reaction that's going to give us the bond dissociation, well, we're going to have to look at C2H6 breaking up into 2 carbons and 6 hydrogens. And as it turns out, we're given the values, the enthalpy values for these, so we can figure out the enthalpy of the reaction. Remember, the enthalpy of the reaction is just products minus reactants. So the products are going to be 2 times the value for carbon, which is 718.4, plus 6 times the value for hydrogen, which is 217.9, and then that's going to be minus the product, or the reactant rather, which is minus 84.7. And once you solve for all of these, you're going to get 2,828.9 kilojoules per mole. So we know the sum of our bond dissociation energies is going to equal this amount. And so one part of our bond dissociation energy that we do know is going to be your carbon-carbon dissociation bond. So since we have 6 of those, it's going to be 6 times 416, and it's going to be times the carbon bond. And since we only have 1 carbon bond, let's just represent it like this. We know that's going to sum up to 2828.9. And if you solve for carbon-carbon, you're going to get that it's about 333 kilojoules per mole. And that is answer choice B. So again, what you need to do is you need to realize that we can calculate the enthalpy change that's required in this reaction if we just take the ethane and just dissociate it into the carbons and the hydrogens. And we can calculate the enthalpy for that, and we can relate that to the bond energies. And since we already know the bond dissociation enthalpy of one of the bonds in the ethane, we can figure out the bond dissociation enthalpy of the other if we just do a bit of algebraic manipulation. So our answer is B, and that is the correct answer. Let's move on to question 23, which says a reaction has an equilibrium constant of 20 at 298 Kelvin, and the equilibrium constant increases with increasing temperature between 288 Kelvin and 350 Kelvin. What may be concluded from these observations? The change in free energy is less than 0 at 300 Kelvin, and the change in entropy is greater than 0 at 300 Kelvin. Well, we can look at that first bit using one of our formulas. So the change in enthalpy, or change in free energy, is equal to minus RT times the natural log of K. Now, this bit is important because we're told that the equilibrium constant increases. So even it's going to stay at 20 or higher. And if we have a natural log of 20, natural log of 20 is going to get us a positive value. And if you have a positive value times 8.3145 times the temperature, which is going to be a positive value, and another positive value, while a negative times a positive is going to be a negative. And so it does make sense for the change in free energy to be a negative number, because after all, the natural log is a positive number. And so A does make sense, and let's look at 2. For the second bit, we can use a different equation. The change in free energy is equal to the change in enthalpy minus temperature times the change in entropy. And the reason we can do that is because we have already concluded that the change in free energy is going to be negative. So we know that it's going to be negative. Another thing that we're told is that as you increase heat, the equilibrium constant increases, meaning more and more products form. And so in what type of reactions is it that as you increase temperature, more products form? Those are going to be your endothermic reactions. And remember, endothermic reactions are have a negative value for the change in enthalpy. And so currently you have a negative equals a negative minus, well, that's going to be a positive, and then we're trying to find delta S. The only case in which all this works out is if delta S is greater than 0. Delta S has to be a positive value, because if it were a negative value, then the negative from the delta S would negate the negative here, and we would potentially end up with a positive value for delta G, which we know that we don't have. So the only thing that really works is if the change in entropy is a positive number, which means that 2 is also correct, and so 1 and 2 are both right answers, meaning our answer is C. And that is the correct answer. Let's move on to our last question, question 24. A sample of water in a movable piston is maintained at 100 degrees Celsius with an external pressure P. Which statement best describes the transformation of some of the liquid water into water vapor? This is kind of weird because it gets a lot into the states of matter. So remember, water is going to be, or some liquid is going to be like here. There's going to be water molecules, or like liquid molecules, and so some of them are going to jump up past the surface and they're going to go into this top area. And at 100 degrees Celsius, the pressure at this top here is going to be 1 atmosphere, as long as we have standard conditions. And so when the atmosphere exerts a pressure, the pressure that's exerted is P. Remember, if the pressure in this container here is greater than the pressure that the atmosphere exerts, then you're going to reach the boiling point. But if it's less, you're not going to reach the boiling point. At P equals 1, well, if the atmosphere is pressuring in with 1 atmosphere of pressure, then you're going to be at this kind of limbo state where if you were to add heat to this system here, then you would reach a boiling point. But if you were to take away heat, you wouldn't reach the boiling point. So really, it's going to be reversible at P equals 1. But if the pressure was great, if it was 2P, well, then you just wouldn't have water turning into liquid water because the boiling point has not been reached. The pressure that the atmosphere exerts on this system is too great. The pressure over here cannot counteract the pressure that the atmosphere puts on it. So really, it's going to be non-spontaneous if the pressure is greater than 1 atmosphere. And so both of those things are going to manifest into answer choice D, which says it is reversible at pressure equals 1 and not spontaneous if pressure is greater than 1 atmosphere. That's answer choice D, and that is the correct answer. That's all I have for this video. I hope you learned something from this whole thermodynamics unit. And I hope to see you next time where we're going to go over kinetics. See you later.